In this long video, or not long, the video is not long, the title is long, we're going to take a look at some things that probably businesses use graph theory for. Let me start with a definition. A Hamilton path is a path that passes through every vertex exactly once. A Hamilton circuit is a Hamilton path that begins and ends at the same vertex. Throughout the rest of this, I'm going to do this. HP will equal Hamilton path, and then HC will equal Hamilton circuit. So as usual, let me start with some simple small examples to try to motivate this, and then we'll go on to more complicated stuff. So very simple. Very simple. There is a Hamilton path where I can just do A to B to C, or I could reverse that path, but there is no Hamilton circuit because there is no way to visit A after I've gone to C, or no way to go from C to A. There's no way back. Still, we have no Hamilton circuit. Let me make that look like a no. But we do have a Hamilton path, and there's several ways that you can do it. You can do A, B, C, just like that. That's one way. Well, or you could reverse it. You cannot do this, A, B, B, C, because the two B's would have been, or the B would have been visited twice. Now, it's sort of weird. A Hamilton circuit, you do begin and end at the same spot, but I guess we don't count that as a vertex that is visited twice. Let me just fix up this last example to make it so it's possible to get myself a circuit. So here's my A, here's my B, and I'll put a loop there at B again, and there's C. So now if I want to do a Hamilton circuit, I can simply go A, B, C, and then come back to A. Or I could reverse that. Or in fact, I could probably start at any vertex that I wanted to and get to anywhere else that I wanted to. But notice that you cannot visit B twice. Next, to facilitate this study, we're going to look at something called complete graphs. And I'll draw a very simple one right off the bat. Now, in a complete graph, every vertex is adjacent to every other vertex. So if you look at the graph that I have here, I have that A and D, or A and B, they are adjacent to each other, but A is not adjacent to C. So the way I can make that happen is drawing one of these, say. So now A is adjacent to C. So A is adjacent to all of the other vertices. However, if I look at B, B is not adjacent to D. And there, B is now adjacent to D. In fact, now every vertex is adjacent to every other vertex. Because if you take a look at A, all the ways that I can leave A are three ways. I can go to B, C, or D. Any one of those, and I can get to another vertex. There are three other vertices. Look at B. From B, I can go back to A, D, or C. There's three things, or three edges shooting out from B. In fact, all of these have exactly three edges coming out of them. That's all you really need, because to be adjacent to every other vertex means that you're going to have the number of vertices minus 1, because if I'm at A, then I'm only interested in at what A is adjacent to. So that's why you subtract the one vertex. So B, same thing goes there. Now, if you try to do the same thing for 5 vertices, let's try this. Draw a complete graph with 5 vertices. And a good idea is to generally arrange these in a circular fashion. And let me label these. I go clockwise when I do my labeling, although there's no rules. You can do whatever you want. So if A is to be adjacent to every other vertex, then I need to draw an edge from A to each of those other vertices. I'll need exactly 4 edges to do that, because there's 4 other vertices. Same goes with B. But notice when I get to B, I've already done the connection from A to B, so I don't need to repeat that. But then I can go to C, but then I can go to D, and then I can go to E. And now notice around B now, we have 4 edges coming off of it, just like A. Now C, I've already got 2 edges coming off of it. I need 2 more. So I'll connect C to D, and then I'll connect C to E. And hopefully you can see how this is panning out. All I need to do now is make the connection D to E. And there I have a complete graph with 5 vertices. Notice that each vertex has degree 5 minus 1, which is equal to 4. Now there's a theorem that talks about what I just mentioned. We have a complete graph. So in a complete graph, with n vertices, there are, not only are there Hamilton circuits, there's a lot of them. There are n minus 1 factorial Hamilton circuits. Now, if you throw out reversals of the ones that we find, removing reverse paths leaves us with n minus 1 factorial over 2 essential Hamilton circuits. Essential Hamilton circuits strip away all the possible circuits that you can come up with and only considers the ones that go into one direction. Reversals of those, as far as counting what vertices you visit, is simply redundancy. Let me do some examples. Find all Hamilton circuits. And I have a complete graph here. My graphs are getting a bit lazy, so let me make these bigger. All right, so now try to look at how we can visit all of these vertices. I'm going to start all of these with A. You can start at whatever you want, it doesn't matter, but I'm going to start all of mine at A. So let's take a look. One simple way to go is A, B, C, D, and then back to A. All I did was go around the outside of the graph. Now, as I come up with these, I'm going to kind of ignore the graph when I come up with all these methods. I am going to instead concentrate on how many ways there are to arrange these letters A, B, C, D, and A again. I want to see how, but I'm always going to start at A and end at A. That means that I have to look at what comes between A, and those are three other vertices. So if you take a look, what I'm trying to come up with, if I start and end at A, you can start and end at any vertex you want. Here's what I have. I've got to visit a vertex, another vertex, and a third vertex before I get back to A. Well, the letters that we have to go into these spots are B, C, and D. Those are three distinct letters. That means there are 3 factorial, 6 ways to arrange the letters. So let's find all of those arrangements. Well, what we can do is we can have, if B starts, then we can get 2 of them with B starting like this simply by switching C and D. And then to get another 2, we could start C, and then to get another 2, we could start D. So all you really have to do is start syncing the B. Now it's second place, right? And now B is in third place. And now you can do the same thing with D. B is in second place, or B is in third place. So those take care of all the 6 in the middle. Let me go ahead and write all these down. I already had the first one before, but now I have A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, and then A, D, C, B, A. So there's 1, 2, 3, 4, 5, 6. And that matches the other ones. Let me just make sure that they do match. This matches that one because the BCD is in the middle. BDC, CBD, CDB, DBC, and DCB. You've got to watch when you're doing these because they can get pretty heavy right off the bat. Even here you can see it requires quite a bit of organization in order to keep track of everything. Now, according to the theorem, there's only 3 essential Hamilton circuits. So what that means is that 3 of these are the reversals of the other 3. So what I'm going to do is I'm going to take this one, and I'm going to call this my first essential Hamilton circuit. Now, if I go down this list, see if there is a repeat of that, but in reverse order. So this went A, B, C, D, A. Now look as you go to reverse. Right here, look at number 6. In its reverse direction, it is A, B, C, D, A, just like I had. So those 2 are exactly the same circuit. Now let's take a look at my next one. I'll call this circuit essential circuit 2. So that's A, B, D, C, A. Now let me see if I reverse it. On the one right after it, I think I have I have to do A, B, D, C, A. So number 4 is the same as number 2. and that is essential circuit number 2 then. So what's left must be circuit 3. And I'll just prove that to myself. If I look at E3 and backwards, I have ADBCA, and 5 backwards, ADBCA. So you can see that the 3 essential ones are right here. And they just happen to be the essential ones that start with A. You can find your own 3 essential ones if you start with any other vertex. It'll be good practice to do such a thing. Now we look at how this is applied to business. Let me start with the definition. A weighted graph assigns weights. They're simply numbers to each edge in a graph. All right, what we have here is a situation where we've measured the distances between each of the major campuses at Tri-C. So as you can see, we have an eastern campus, we have a metro campus, we have a western campus, and we have a district office. Now, I know I've not drawn them according to the way things should be pictured, but as I said, whenever you're going to draw such a graph like this, it's a good idea to put them in a square or circular fashion. So I'm going to make all of my connections. Like so, and let me get the mileage down. Start with Eastern Campus. Eastern to Metro is 17.2 miles, so I'll put that there. Eastern to Western is 20.4, so let me put that there. Now when you're labeling these, try to label it so that you don't confuse where the numbers go to. Eastern to District is 17, and then I've taken care of Eastern. Notice that I've also wiped those out too. Now let me go on Metro Campus. So Metro to Western, M to W is 10.1. And then M to District is 0.8. So obviously these are not physical. The graph, the picture itself, does not physically represent the situation, as M and D should be the closest to each other. So I've got Metro taken care of. Let me cross those out. And now go to Western. W to D is 14.5. Got that, and that takes care of all of them. All right, now usually what you try to do here is come up with what they call an optimal solution. That means a solution that involves the smallest total sum of all the edges that you use. In fact, that's the nature of the traveling salesman problem. The salesman is going to try to visit everybody, get back home, and do it probably using the cheapest method, or at least maybe the least mileage. That's what we're going to look for here. So let's first get all the possible solutions, and that's a matter of looking at all the possible ways of arranging the letters. Since you can start at any edge, any vertex that you want, I will start all my vertices at E. Not only that, there are 4 minus 1 factorial over 2. That's equal to 3 essential Hamilton circuits. And if you take that and take 4 minus 1 factorial, that's equal to 6 Hamilton circuits. So this is going to partly try to show you how to arrange your things. So I can start wherever I want. Like I said, so I'm going to start all of mine at E, and I'm going to write all 6 of them out and then we'll remove the reversals. So let's go ahead and start with E blank 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 E. Same with the next one. All right, now the letters that we have between the E's are going to be all the possible ways, all the possible arrangements of the letters MWD. So I'm just going to start looking at that, MWD. Now you can start to count these in your head. If I do the next one, EM, I'm going to have DW. And that takes care of all those little threes that have an M to begin with. Then you can have an M in the second spot like this, but then reverse the D and the W, and that's all the ways with M in the second spot. And then we'll have all the ways with M in the third spot. You're going to have WD or DW. That's all of them. Now let me get the totals of these weights. So I'm going to do this in some detail so that subsequent examples I don't need to do in such detail. So let's start with circuit number 1, E, M, W, D, E. All right, so we start with path number 1. Let's add them all up. Here I have EM. EM was 17.2. And then MW. MW, 10.1. WD, 14.5. And then DE, 17. Add these all up, and what do you get? $58.8. All right, this time I'm still doing MD, so that's 17.2. But now when I do, or EM I mean, now when I do MD, that's different. I'm going to have 0.8. And I'm going to have DW, 14.5. And then WE, which is 20.4. Let's see what this adds up to be. $52.9. Let me see what the next we have. I'm just concentrating on the letters in between the E's. So for number 3, we have WMD in between. All right, let's take a look at what. No, now we're doing EW to start. So EW, I'm going to start on 20.4. And then I'm going to do WM, which is 10.1. And I'm going to do M to D, which is 0.8. And then D to E, which is 17. And I got 48.3. Now, this is interesting. Notice that I have 3 different numbers. What that means is if I try to do the next 3, I'm going to get the exact 3 numbers again. Let me show you what I mean. Let's take a look at number 4. We have E, DMWE. Let's just look at this one. ED, which is going to be 17 to begin with. DM, which is 0.8. And then MW, which is 10.1. And then WE, which is 20.4. And you see what happened? This 4 is the reverse of 3. These 2 are reversals of each other. So here's the game. I know that I am only going to find 3 essential Hamilton circuits, and that 3 of them will be redundant. Since my first 3 shots were 3 different numbers, I know I have all essential Hamilton circuits because of that. And in fact, look at this guy right here. This is our cheapest. That's our cheapest way to go. And what we have here, we have 48.3. We call this the optimal solution. So that's what we're looking for. Usually it is the smallest number. Now, these numbers don't have to represent mileage. They can represent just about anything, whatever is meaningful to a company that is using this to model their situation. Right, this next example involves us doing errands and trying to get to Best Buy, Lowe's, and Lube Stop, and then get back home, of course. What I'm going to do just to help myself out is I'm going to call Lube Stop just by the letter S, and then I'll use the first letters of each of the other ones. So I have H, B, S, and L. Basically, all I want to do is look at all the possibilities, essentially look at all the possible arrangements of the letters. If we're starting at home and ending at home, then we should probably start and do this kind of stuff. So there's going to be 6 ways to arrange the 3 letters between the H's. So there's my first one. How did that go? That went from H, B, S, L, back to H. So it just went around the square. Yeah, let me go ahead and calculate them on the spot. So H to B was an 8.0. Then we had B to S was 5.3. And then S to L was 0.3. And then L to H was 3.1. Probably shouldn't put so many plus signs. There's one. Then number 2. So the way I'm doing it again is I'll start and end at H. Now I'm looking at the B, S, and L. I can still have B as my second one. All I got to do now is switch L and S, and I get another one. So let me go ahead and do this. H to B is still 8.0. B to L is 4.4. L to S is 0.3. And then S back to home is 2.7. And I get 15.4 that way. And then for my third one, I'm going to put my H's on the outside. And now look, I have all the ways where B came in second place. So let me pick another letter. This time I'll do S. And then I can do BL. And then the next one I'll do would be LB. But let's go ahead and do HS. That's 2.7. And then BS to B is 5.3. And then B to L is 4.4. This way almost seems like it's trying to find the longest way to get there. And then finally, L to H is 3.1. And we end up with 15.5. This is beautiful. I don't even have to bother doing the other 3 of them because I have 3 different numbers right now. That means they have to be 3 completely different circuits. So which is my best one? This guy right here. That is my optimal solution. This will be the last example I do, and I'm not exactly sure how beneficial it's going to be because you're going to see that very quickly these graphs become very complicated. That's why massive computers are used to solve these problems. They're generally hundreds, if not thousands, of vertices hanging around, and our brains just cannot do such computations as necessary to do them. But that doesn't mean these small problems aren't worth looking at, because a lot of times you take an incredibly complex system and you're able to break it into smaller problems, and you can apply this kind of thinking to them. So what I'm going to do is this. I'm going to start all of mine at B, and I'm also going to end mine at B. So I will have, between B and B, I will have to visit H, I will have to visit R, I will have to visit S, W, and then come back to B again. So what I'm going to do is I'm going to write all of those down and what their total value is worth, or total weight, I think is what they call it. All right, what I've done is written out the 6 essential Hamilton circuits. If you go and attempt to find any more, you will, but they will simply be reversals of this. How many do we need? If you look at, we have 5 vertices, we subtract 1, factorial over 2. This is how many essential Hamilton circuits that we have. So that's 4 factorial over 2. That's 24 over 2, which is equal to 12. I misspoke when I said there was only 6 of them. There's 12 of them. So I still need 6 more of them. What I have done, let me explain my thinking. Let's look at the first one. I had BHR, and I knew I had to end with a B. So in between BHR and B, I had SW. There's only 2 ways to arrange them, SW or WS. So those are all the ways that I can start with BHR. Then I moved on to BHS. And the odd letters out that time were R and W, so I did RW, WR. That took care of the BHSs. Next, I'm doing the BHWs. RS, SR. Those are the BHWs. Now let me move on. What I have done in all those 6s then is I have taken care of all the ways that I can go from B to H. So let me pick different letters now to start. So instead, I'm going to pick, instead of H, I'm going to pick BR. Now the letters left over are H, S, and W. And then B. I know for a fact that I'm not repeating something, because now there is no situation, if you reverse any of these things up here, there is no situation where an H occurs in the 3rd letter going that way. So all the ways with an H in the 3rd position, I know I'm going to be in good shape. So I have B, R, H, and then I can move the S and the W around. So I have B, R, H's. Then I can now move on to B, S, but with H in the middle spot. And then I can do the same. I'm running out of room, but then I can do B, W, and have an H in the 2nd spot, in the 3rd spot, sorry. I know I'm always going to end at B. It's just a matter of arranging the 2 letters that are left. So if I've used B, S, and H, that leaves R and W. So I can do RW, but then I do WR. Now if I have B, W, H, then that leaves S and W. So I mean S and R. So I'll do RS, SR. And this gives me the other 6. So now that I have all 12 essential Hamilton circuits, I just need to find the smallest one. That's that one right there. And I think I made a mistake on it, actually. So I have my optimal solution. Now the problem, I just pulled this out of the textbook, and I didn't even talk about the implications for what this has. This basically, the H stood for home, so conceivably you would have to start and end at home, but I don't care about that. I'm going to show you a way around that anyways. Now, let me show you a way to approximate the solution. This is an approximation. It's called the nearest neighbor method. basically, what you do is you find the cheapest, lowest expense way to start. And if we look at all of the edges in this graph, you'll notice that B to S is absolutely the smallest possible one you can have. So there's BS. I'll put that in there. And while I'm doing that, I'm going to keep track of how much I'm using. Now, the nearest neighbor method is very simple after this. Next, all you do is find the cheapest way in and out of every vertex. So from S, I have to go to another vertex. What is the cheapest way to leave? And it looks to me like I can go H 11.6, or I can go to R at 11.4. That's even lower. So I'm going to put an R next, and let me put my 11.4. Now remember, you never want to go back to B to the end. Sorry, R can go to H or W. R to W is 15.2, R to H is 18.1. So I will take the 15.2 and go to W. So I'm just choosing the cheapest way each time. Now W is going to have to go to H. Because I'm not going to go home yet. W to H is 15. Be careful with that. And then I have no choice but to go home after I do that. Sorry, I go back to B after H. That's 12.8. And what do I get? Now, according to the problem itself, it was a physical problem, and H represented home. We want to go and start and end at home. So what I'm going to do is I'm going to start this at H instead, and then just follow the letters as I have. So the next one was B. Don't put two B's in a row. You can't do that. Then the next one was S, then R, then W, and then H again. Now let's take a look at these costs. HB was 12.8. BS was 10.8. SR was 11.4. RW was 15.2. And then W to H was 15.0. Let's add them up again. So you see, any method, any solution that you can find using whatever method you want can be refound, but instead start at any vertex that you would want to. This really would be our optimal solution because this starts and ends at home.